Lecture 18 covers section 6.2 through 6.3. At the end of today's lecture, you should be able to understand the operation of an operational amplifier. And you should be able to understand and apply the two main assumptions when modeling our operational amplifiers, as well as the three requirements for an operational amplifier to operate in our linear range. Below, we have a schematic of an operational amplifier. What we see is we have an 8-pin op-amp, where we have a scallop on the top of our op-amp that allows us to determine the orientation of our operational amplifier. Now for this particular operational amplifier, we have a no connection pin in our top right, we have an offset null in our top left and bottom right, we have a -15 and +15 voltage source to our system, and then we have an inverting, non-inverting, and output terminal. Operational amplifiers are quite unique, for early analog computers used these devices for mathematical operations, namely addition, subtraction, multiplication, and division. Operational amplifiers are also very useful for providing gain, i.e. amplification, or attenuation, i.e. a reduction of signal, for filtering a signal, or comparing two signals. An operational amplifier needs some power supply, and this is designated by our -15 and 15 volt potential within our system. However, we're not concerned about the power supply of our operational amplifier, rather we're concerned with our non-inverting, inverting, and outputs of our device. Now, to analyze operational amplifiers, we are almost always going to use Kirchhoff's current law. Once in a while we may use KVL to relate a voltage within our system, but KCL is going to be our primary method for analyzing the behavior of these devices. Now, if we break down our schematic into a circuit diagram, we can represent our operational amplifier as follows. We have a few unique characteristics. The first is our -15 and +15 sources. That is, we saw previously, we had a -15 voltage source on our left and a +15 voltage source on our right that would supply our voltage potential to our operational amplifier. Now when we analyze our circuit, we're not too concerned about this external voltage being supplied to our system. Therefore, we typically ignore it. We see we have an inverting terminal. Our inverting terminal is associated with the negative polarity of our operational amplifier, where we have a voltage potential between our input and ground designated as V1, where we have current I1 entering the negative terminal of our operational amplifier. We also have a non-inverting terminal. Our non-inverting terminal is associated with the positive polarity of our operational amplifier, where our polarity V2 is measured between our input terminal and ground, and we have current I2 entering said terminal. Lastly, we have our output terminal, where we have a voltage output that's measured with respect to ground, and we have I out entering our output terminal. This is done by convention. Now we can take the schematic and reduce it to what we're actually concerned about. That is, we would have V1 existing at our inverting terminal with I1 entering. We'd have V2 existing at our non-inverting terminal with I2 entering. We'd have V out existing at our output terminal with I sub naught entering. Now to analyze behavior of an ideal operational amplifier, we have to make the following assumptions. The first is our voltage potential at our inverting and non-inverting terminals are equal. That is to say, V1 is equal to V2. We also assume that our current entering our inverting terminal is identically equal to our current entering our non-inverting terminal, and we will assume these currents are 0. Per assumption 1, we rationalize that our output per input, i.e. the gain of the system, is going to be much larger than the input, such that any difference in between our inverting and non-inverting terminals cause a major change in our output voltage. We do not want that. So we assume that we have the same potential at our inverting and non-inverting terminals. For our second assumption, when we assume I1 is equal to I2, which is equal to 0, in actuality, our current entering our operational amplifier is going to be on the order of nanoamp. That is 10 to the minus 9th amps, which is relatively small. We do not need to take that into consideration within our calculations. Now, for our operational amplifier to obey these assumptions, i.e. for it to be within our linear range, such that we can assume ideal behavior, the following must be satisfied. The first is the magnitude of our output voltage has to be less than our saturation voltage. The second is the magnitude of our output current has to be less than our saturation current. And the third is the absolute value of the time rate of change of our output voltage has to be less than our slew rate. Now these three variables, VSAT, ISAT, and slew rate, are given by the manufacturer and differ for each operational amplifier. That is, we would have to know which operational amplifier we are modeling and look at the technical documents to pull these values to make sure that the operational amplifier is going to obey these three requirements. Now, for DC systems, everything we have done thus far in this class, our item number 3, i.e. the absolute value of the time rate of change of our output voltage, is going to be automatically satisfied. For our output voltage does not change as a function of time within a DC circuit.